Hello, I am Roberto Vasquez from the Institute of Astronomy of UNAM in Ensenada, Baja California, Mexico. We will continue with our Mezcal workshop, focusing on the use of the Mezcal spectrometer located at the National Astronomical Observatory of San Pedro Martyr. This instrument allows us to study the kinematics of gaseous objects such as planetary nebulae with the aim of obtaining their morphokinematic structure. Following that, we will proceed with the basic processing, which in this instance involves the calibration of the wavelength in our spectra, ensuring accurate measurements and precise analysis. Firstly, I would like to mention that we should make a transition towards the task category known as long slit or long slit. So let's not outspec long slit. We would also require a file containing the identified lines around the filter we are presently utilizing for our analysis purposes. I would like to recommend you to visit the San Pedro Martyr Observatory. Here is a link to their website so that if you are using specific data from Mezcal, you can obtain that kind of support from there. It can be really helpful for your research. So in our particular situation, we will make use of the H-alpha N filter, but here is the website of the observatory following the exact same link I just sent you so that you can have a visual examination of the spectra. In this case, we are talking about a spectrum around the sulfur-2 lines. This is the H-alpha N. This is the one we are going to use. And I also show you the oxygen-3, which are, let's say, the fundamental tools, the basic filters we use for planetary nebulae. What is the wavelength calibration process? The procedure consists of 4 steps. We are going to identify the spectral lines of the comparison arc. That is, we are going to work on this process consistently. During the comparison arc, we will identify the lines present in that spectrum because either the software will provide us with the coefficients of a polynomial to adjust all the lines, or we will manually analyze the data to determine the necessary adjustments for each line in the spectrum. Subsequently, the process of reading identification utilizes the polynomial we have provided to accurately identify the lines in both the forward and backward directions of the text. And if you recall, we have previously discussed how a certain aspect of the design of this spectrometer leads to a deviation in the x direction of the lines, causing them to form a kind of arc, a curved shape. I am referring to the curvature of the spectroscopic lines, not the arc of the lamp. This deviation in the x direction results in the lines appearing curved, resembling an arc rather than a straight line. So the Ray Identify command is a tool that will assist us in re-identifying the spectrum despite any distortion, and this is something that will be corrected at a later time, once we have the required information and resources to do so. The fit course command will execute a 2-dimensional adjustment where each of these polynomials will move up and down from the midline, forming a function that allows us to make a transformation from R to R. This function is particularly useful for wavelength calibration as it corrects any deformation of objects behaving like the comparison arc. By applying this adjustment, we can ensure accurate calibration and correct any distortions in the data. The fit course command is an essential tool for achieving precise and reliable results in scientific analysis and measurement. Remember that it's not just about recognizing where the lines are, but also keeping in mind that there is an effect where the dispersion is not uniform when observed directly. So we need to build it, create a uniform dispersion based on the information we have, straighten the spectral lines, and then we will have a very neat, very nice spectrum with excellent clarity and precision. The ultimate command is transform, which precisely applies the 2-dimensional function created in fit course to the input image we provide, ensuring accurate and reliable results. So, since we will initially use the comparison arc, we will transform the comparison arc, and that transformation will be very evident. We will be able to confirm that everything is correct in order to then apply it to the spectrum of our object, because sometimes object spectra are not very easy to observe as they are distorted. But that distortion must be applied because it will allow us to learn very important things, like the velocity of the object and its components, etc. So it is extremely important that we are able to perform this step initially with the arc, and once we are convinced that it is correct, apply it to our object spectrum. Here is a comparison arc. As you can see, this arc indeed has intense lines throughout the spectral range and also has this slight arched deformation towards the ends. Please remember that if it deviated even a little from the optical axis, this deformation would accumulate over time, resulting in an increase in the wavelength. Therefore, it is crucial to correct any deviations to ensure accurate measurements. By addressing these deviations, we can maintain the integrity of the spectral data and obtain reliable results. Note that these arcs also contain cosmic rays. I typically do not eliminate them due to their sporadic nature, which does not result in significant interference. However, it could be problematic if a cosmic ray were to fall in close proximity to one of the lines and alter the wavelength, potentially leading to issues for us. So if you feel comfortable and it doesn't take much time for you to correct the arcs for cosmic with the cosmic, I don't see any problem, but personally I don't like it. If I don't need to do it, I don't like doing it, and I haven't had any issues with that. Okay, this is the identify command, correct? So let's input the name of our image that contains the arc and retrieve the relevant information we need. There are several places where the initial cut can be made. One of the defaults is to be the middle line, meaning that the middle line will be used, the one that is close to the optical axis, and from there it will identify, well, first there will be a cut, and it will identify the lines there. The numbers I leave there are basically the default ones. Sometimes there is talk of having a file containing the spectral lines. In the case of Mezcal, I don't think it's so important because there are few lines, less than 10 lines that we are going to identify. So I like to do it by hand because I am very sure of what line was identified and how. Once the identify program is executed, it accurately displays the discontinuity in the spectrum. If you observe the section below, it contains pixels and it is not calibrated in terms of length. Therefore, one must navigate to each of those lines, input M using the command, remove the red cursor by typing M, and then a yellow line is placed where the wavelength of a line is entered. Subsequently, I proceed to input NM at the location of a spectral line, followed by entering the corresponding wavelength value. So once we have some lines, we can add an F and it will make the adjustment, and well, we can play around. If I don't like the adjustment, I can delete lines, add others. In short, check if I made a mistake. If we have good statistics here, for example, if we give it a Y, and if we are in it, we can give it an F. Sorry, the F. And after the F, we give it an I, and JK will show us different uncertainties in different parameters. One of them, the most important when we want to extract the kinematics, is the velocity. So the velocity is also calibrated in that spectrum. Here, look, it's much less than plus or minus 0.1 kilometers s. It's a very good calibration of the lines that are there and the ones we provided. When we're already happy, we do Q, and then it'll ask if we want to record this in the database. And we affirm our agreement, and that is the end of it. One aspect that has held great significance for me is the creation of this command located below, which involves duplicating the identification file generated by this command, referred to as ID. I will duplicate the file using the same name, but adding the suffix back, and this will prove to be beneficial in case any errors occur and I need to re-identify. In such situations, I can simply rely on the copied file. This file, the one that is not backed up, is rewritten in the next step. So if there is any error in the next step, I simply copy the backup back, and it's as if the second step had not been done to see what I need. Well, the second step is the re-identify. And then we set as the reference image the same one that we are going to re-identify. One of the important things that I include here is this parameter that says verbose output. The default is no. I set it to yes because it will show us what it is doing, which is taking this identification and then gradually moving it up and down the line. So, well, and this is precisely what Server Bauges produces. It provides us with information about each section that was being done, right? It accurately tells us the details of every task that was carried out. How many lines were identified, how many lines were lost, and then in some way it also gives us information about the shift that had to be corrected in order to precisely establish the two-dimensional parameters that will help us in the next step to create a two-dimensional function. As I was saying, the results are rewritten in the existing file. If everything is fine, if there were no disruptions, we continue. Okay? Well, the next step is the fit course, and in the fit course, we have to be very careful with what we input. The input image, the same image, has not been altered yet. In the field where it says coordinator feed name in the database, do not input anything. I used to make a lot of mistakes there at the beginning, but absolutely nothing should be entered because a new file will be created. So for the interactive adjustment, I choose yes because that way we can play around more or less, and here we would try to create a Chebyshev function of order 6, both in x and y, and well, it should pass through all the points. So we run it, and it will show us a display that we can view in various ways. For example, here it can show us the comparison line map. If we input XXYY and then run it with an F, it precisely shows the deformations it found and will correct with the function that will be created. Other things, for instance, we can also observe the X-ray residue map, which is highly fascinating in this context because it reveals that around 0, there are fluctuations that might arise as a result of certain wavelength recognition in the various small rows. And when there is an extremely unpleasant value, it is typically due to the error of some cosmic or similar phenomenon that was left unresolved, correct? So in the event that it throws me some extreme value, then those extreme values, like the one in the top left corner, could in some way be eliminated or disregarded. You place the cursor over the D and remove it, and then it won't be included in the statistics, okay? You won't use it for anything at all. The same when we exhibit the residual map as a function of y, and indeed everything is centered around 0, as can be observed visually. And well, that's it. So there, when we are happy, we come up with Q, we say yes, I don't know what, and it creates a new file for us that now, instead of being called ID file name, it will be called FC file name. And that's the one that will serve us for everything. Here it is, precisely when we zoom out. Here is what tells us how the mapping was executed and tells us the wavelength found at each corner. And as you can see, there is a minimal disparity in wavelength at the top and bottom of the left end, and at the top and bottom of the right end. When these numbers are extremely different, 5, 10, 15, 20 angstroms, something bad happened. When there are small differences around 1 angstrom, 2 angstroms, it means we are doing well, because not necessarily when we have our spectrum do we necessarily end and start in the same place. So, this image gives me confidence to say that, well, we're doing well. Okay, so now you press yes and record the function. And finally, the last step is the transform. In the transform, I would advise you to be extremely cautious with 2 specific aspects. The names again, the initial name is the same as we have been using, but for the output name, we need to add something now. I placed a W for web calibration. And it is extremely important that in the section where it indicates names of coordinate feeds and the database, they must match exactly with the input name. That is going to be of utmost importance because that is the one providing us with the information about the two-dimensional function that will be applied. And here, of course, we'll apply a function from the same object. That's why the three names are very similar. So, essentially, the initial name is established, but be cautious, because in the subsequent step we are about to undertake, we must maintain that name even if it is a different input spectrum. All right? But I'll explain it to you right now. So the input name goes there. The input name where it says names of coordinates. And the output name is to add that W or any other letter to indicate that it is already the spectrum calibrated in length. Okay? So we provide it with 1, 2, 3, 2 points, proceed, let's proceed. And at this very moment, it is going to display to us in a small square image what the value of each pixel is, both on the left and right sides, at the bottom and top, and it is going to inform us about the dispersion. In the case of X, which is of utmost importance to us, there exists the wavelength, the initial one at 6542 angstroms closed, the final one at 6592 angstroms closed, and zero dispersion, with a precise measurement of 101 angstroms per pixel. That is the pixel scale, okay? In this case, the dimensions of my image are 500 by 500 pixels. In the case of Y, there is no calibration, even though we know the spatial spectacular scale, but there is no calibration there. It's pixels, 500 pixels. And so, let's proceed to the matter we are here to work on, which is the most important thing, or the important thing, namely wavelength calibration. Okay? So that's it. Then it tells us what the dispersion axis is. Obviously, the software already knows, is the 1, and it sets it to 1 by default, and we press enter. There are spectra that for some reason come out at 90 degrees when the CCD is flipped. Well, it has happened to me at some point. Almost not anymore. It is no longer a free parameter, but at some point it happened to me, and then the spectra can be reduced with the dispersion axis 2, which would be the vertical one, and nothing happens. In the end, we can work with all of that. All right, so once the comparison arc is transformed, this is what it looks like, okay? On the left-hand side, we have the original comparison arc, and on the right-hand side, it is already calibrated and prepared for use. Upon examination of the lines at this moment, it is evident that they all exhibit a straight appearance. However, it is not just that. The dispersion on the spectral scale has now achieved uniformity, resulting in a fixed value of 0.0100 angstrom per pixel. Take note of how now that you have acquired that, you are able to occasionally manipulate a tool from SAW Image or any other relevant resource in order to visually assess whether the lines are genuinely straight or not. Indeed, one can perform that action. I positioned several boxes in the presentation in order to actually experiment and meticulously analyze that the spectral lines are genuinely straight. On the right side, suddenly they see some areas that are kind of dark there, unusual, but don't worry, it's because the intense line was actually very intense. So when splitting it, there will be dark areas left, but it's okay. If one generates spectra or calculates what the maximum is for that spectral line, it will perfectly and satisfactorily match the wavelength it should have throughout the entire spectrum. So that is simply just an appearance of something, but it is not a problem. I mean, the calibration is done correctly and accurately. So, once we are satisfied with the obtained function and the transformation of our comparison arc, the next step is to now transform our nebulous spectrum, from which we remove cosmic rays, apply bias, trim it, remove the bias, eliminate cosmic rays, and then proceed with the transformation. We will calibrate the wavelength as the final step, the transform, using the arc for the entire calibration process to generate the function that will convert from pixels to wavelength. So the only thing we need to execute is the transform. If you observe there, the input file is different because for the spectrum file, I use the W as the output, but in the location indicated by the big red arrow and the I, that file name is identical to the arc, because with this command we are instructing to utilize the transformation function you acquired with the arc, alright? Because that is the one we are going to apply. So that is why in Mezcal we take an arc after each slit. In the event that there were any flexion issue that slightly altered the dispersion, we would not be able to make use of another arc. That is the reason why we usually opt to use arcs with each of the spectral lines. And that is the end. Once applied, here we have the before and after images for comparison. Notice that in our spectrum without cosmic rays, the lines in the sky appear curved, and here in the new spectrum, the lines in the sky appear straight. They look straight, so this means that it is perfectly calibrated. An additional command or processing that is no longer as important, but allows us to work better, is subtracting the sky lines. We cannot subtract the stars because it's important for them to be there. Sometimes they tell us things. However, if the skylines are part of the atmosphere and can be removed without any issue, we need to run the background command. The background command will give us the same with an input name that is already wavelength calibrated, and the output name I put as S for sky and the intervals that are there. 2 intervals can be given, more than 2 intervals can be given, usually above and below where our nebula is, where there is no rare emission. In our case, for example, I was excluding it prior to reaching the stars, specifically by considering this interval and not addressing this halo that we are aware is a reflection. It entails taking an interval here, the y value, and taking another small interval here prior to reaching the stars without making contact with either the stars or the halo. This is done so that the program can interpolate the straight lines, known as the sky lines, using this information and generate an image that is identical, except for the subtraction of the sky. That would be approximately the same as what it would be in this processing once we execute it. Over there on the left-hand side, you can observe the spectrum calibrated in wavelength with its sky lines. And on the right-hand side, we observe the spectrum without the skylines. You can observe that there are the stars, correct? There is the halo, the skylines simply disappeared. Then, as we're done here, it's over. It's ready. So, what I did was take the nitrogen 2 line that's there, the nitrogen line 6583, which always provides us with a lot of information about the kinematics of our objects. And well, I displayed it, zoomed in, and there you can see very interesting things in the spectral line. You can effectively see that there is an expansion, like an ellipse, but there is also internal emission, meaning there is emission that is not moving and emission that is expanding. Additionally, at the top and bottom edges, there is also intense emission. So it will be fun to try to see what this nebula is, what structures this nebula has, why they are, and at what speed they are moving. We can already ascertain all of that information through the calibration process of our spectra. So, well, this is the end. So what comes next is to start practicing. That is, taking spectra and doing all the processing. And we still have one more class left that deals with modeling these lines. That is, how we obtain the physical information and then how we model to have a greater understanding of our object, what the kinematic structure is, the object, and all the science we can discover in the process. This will enable us to gain valuable insights and expand our knowledge in the field of astronomy. So for the moment, I will conclude this class at this point. Let's await the next one, and I express my gratitude to you for your kind attention. If you have any doubts or questions, please feel free to get in touch with me or the members of my group. I am confident that we will be more than happy to assist anyone who needs help with problem solving. Additionally, if you have any corrections or suggestions for improvement, we are also open and willing to consider them. So for now, thank you very much for your attention. See you next time. Thank you.